For the last module in this chapter, let's go ahead and talk about the Arrhenius equation. The Arrhenius equation actually allows us to determine the activation energy for a reaction. So as a reminder, what am I talking about when I talk about rates of reaction? Well, first, things like temperature can increase the rate of reaction. So can concentration and pressure. We see as we increase the temperature, the concentration, the pressure, the rate of reaction increases. So how does the increase in the temperature increase the rate of reaction? Well, one thing you need to understand is that increasing temperature does not change your activation energy. At higher temperature, more molecules are able to collide with sufficient energy to get over your activation energy barrier. So if I'm looking at temperature, the fraction of collisions with a given kinetic energy versus kinetic energy, T1 and T2, if T2 is greater than T1, I see that the minimum kinetic energy needed for the reaction to occur is more likely going to be hit by that large temperature. So again, the size of the shaded areas under the curves are proportional to the total fraction of collisions that involve the minimum activation energy or more. The minimum kinetic energy should come from the kinetic energy of the molecules before the collision. It's converted to potential energy to break the bonds and change the arrangement of the atoms themselves. So looking at the fraction of molecules, higher temperature, more likely to be able to react. The Arrhenius equation. The Arrhenius equation is K is your rate which is your rate constant at temperature T, is equal to A, a pre-exponential term, we call this your frequency factor, raised to the negative E sub A, your activation energy, and that's in kilojoules per mole or joules per mole, depending on which units you're using, divided by R, your gas constant. Units can be 8.314 joules per mole K or 8.1314 times 10 to the third kilojoules per mole K. That is dependent upon this, and temperature in Kelvin. And that is log-based. E is the base of the natural logarithm, so 2.78. We can rearrange this equation. There's an easier form to use for the Arrhenius equation, where we find the natural log of K2 over K1 is equal to negative E sub A over R times 1 over T2 times 1 over T1. This is if you have two different rate constants and two different temperatures. You can derive this equation. I'll write it out here if you want to see it. So if we take this equation and take the natural log of both sides, the natural log of K is equal to the natural log AE negative E sub A over RT. So natural log of K equals to the natural log of A minus E sub A over RT. Rewrite that. Natural log of K is equal to negative E sub A over R. I'm going to pull out T times 1 over T plus the natural log of A. This gives me the form y equals mx plus b, which allows me to get an Arrhenius plot. I can also continue this process. The natural log of K2 would be equal to the activation energy over R of 1 over T2 plus the natural log of A. Natural log of K1, negative E sub A over R times 1 over T1 times natural log of A. Really running out of space here. If I take the natural log of K2 minus the natural log of K1, this would be equal to E sub A over R times 1 over T2 minus 1 over T1. It's the same as saying natural log of K2 over K1, negative E sub A over R times 1 over T2 minus 1 over T1. And I apologize, this is so messy on this slide. But that's how I get the 2-point form. But so you can get a 2-point form, or you can get the Arrhenius plot equation, whichever one you want. I don't really care. But they're both useful to me. Why are they both useful to me? Because I can find activation energy. If I plot natural log of K, negative E sub A over R, 1 over T, plus natural log of A. Again, y equals mx plus b. So my intercept here is the natural log of A. My x-axis is 1 over my temperature. My y-axis is my natural log of K. My slope is negative E sub A over R. I can actually determine my activation energy straight from this slope by graphing the natural log of K as a function of the reciprocal of the temperature. I could do this, or I could give you K values, temperatures, and have you calculate the activation energy there as well. Rate law connections. The rate is equal to K times A to the value of X. X is your order with respect to A, must be determined experimentally. The rate of an elementary reaction is directly proportional to the rate constant K. The rate constant K is exponentially proportional to the temperature. The rate constant K is directly proportional to the success of the molecular reactions. These are all connections that you need to be able to make. So again, your rate constant K, directly proportional to the rate of the elementary reaction, exponentially proportional to temperature, directly proportional to the success of the molecular reactions themselves. And lastly, let's work 2 last examples. Nitrogen tetroxide N2O4 decomposes to nitrogen dioxide NO2 in a first-order process. If K is equal to 2.5 times 10 to the third seconds to the minus 1 at negative 5 degrees C, and K equals 3.5 times 10 to the fourth seconds to the minus 1 at 25 degrees C, what is the activation energy for the decomposition for this reaction? I'm trying to find E sub A. I'm told K1 is equal to 2.5 times 10 to the minus third seconds to the minus 1 with an initial temperature of negative 5 degrees C. Convert that to Kelvin, please. 268 K. K2, 3.5 times 10 to the fourth seconds to the minus 1, 25 degrees C. And please also convert that to Kelvin, 298.15 K. And technically by sig fig rules, this should be 268.15 K. Then I'm going to use my 2-point equation. ln of K2 over K1 is equal to negative E sub A over R times 1 over T2 minus 1 over T1. Natural log 3.5 times 10 to the minus fourth seconds to the minus 1 divided by, hold on, did I write those down? 3.5, oh yeah, okay. 2.5 times 10 to the third. That should not be a minus sign. That's where I'm messing up. I apologize. Too many minuses when I'm writing these things out. I'm so used to writing minuses. Positive. 3.5 times 10 to the fourth seconds to the minus 1 divided by 2.5 times to the third seconds to the minus 1 equals negative E sub A over R, 8.314 joules per mole K, times 1 over 298.15 K. And I am absolutely running out of room. Minus 1 over 268.15 K. Solve for activation energy. E sub A. 58410 joules per mole. Sig figs are here because there's 2 sig figs here and 2 sig figs here. And you can convert that to kilojoules if you would like. 58 kilojoules per mole. So the activation energy of that reaction, 58 kilojoules per mole. Second example, for the reaction N2O4 going to 2NO2, at 30 degrees C, K is equal to 5.1 times 10 to the 6 seconds minus 1, and the activation energy is 54 kilojoules per mole. What is the value of the rate constant at 45 degrees C? We use the same equation. T1, 30 degrees C plus 273.15 gives me 303.15 K. T2, 45 degrees C. That one just says 45. So 45 degrees C plus 273, 318 K. You're going to use the same equation. So ln of K2, which is what we're trying to find, negative 5,400, or 54,000, I apologize, kilojoules per mole for your activation energy. Joules per mole. Because I'm going to use 8.314 joules per mole K. You can either keep that in kilojoules, convert R to kilojoules, or convert it to joules. I convert it to joules. I don't care which one you choose. 1 over 318 K minus 1 over 303.15 K. Plus natural log of K1, which is 5.1 times 10 to the 6th. If you're unsure how I undid that, remember that the natural log of K2 divided by K1 is equal to natural log of K2 minus natural log of K1. So then I added K1 to both sides. So that's your log rules coming back into play. Natural log of K2 equal to 16.46. Raise everything to the power of E. K2 is equal to 1.4 times 10 to the 7th seconds to the minus 1. So you can use that equation to find activation energy or to find a K value. You can also find a temperature if you want to solve it that way. Hope this helps.